So let's discuss the cross product. First, some information. Basically, we'll go over like the dot product a little bit, this time a little bit more in depth still, because the cross product is a little bit more complicated. So it is a vector, it's not a scalar. So u cross v, these two vectors will create a vector itself. Yeah. But yeah, this definition is not really used in this course too much. You're not going to use this all the time, depending on how Calculus 3 is structured, but usually you use this way that you calculate stuff using this method. We have defined it in terms of I, j, and k, the vector, and you go from there. But the determinant, this is called a determinant. This 3 rows, 3 columns structure is a 3 by 3 determinant. You know, if you have the vectors u and v as such, you get this creation. And there's also the triple scale, you know, basically this is what the cross product is equal to. Up here is what it's equal to, but it's also what it's equal to. So the triple scalar box product is given by u cross v, you know, dot w, and it's a scalar product. It has three different vectors, but you end up with basically the volume of a box if you get the magnitude of it, and it can be set up like a matrix like this as well. 3 by 3 matrix, but a little bit differently. But it's not the most important thing ever. Here's something, how to evaluate a determinant. If a 2 by 2 determinant, then you basically just do, you do one side minus the other diagonal, one diagonal minus the other diagonal, you multiply the diagonal minus this other multiplied diagonal. 3 by 3, there's two methods that work, two solid methods that work for this no matter what. 3 by 3. Okay, so a 3 by 3 determinant. Then we have like x1, x2, x3, y1, y2, y3, and z1, z2, z3. Instead of let's just say like we have these, just because this in general work. I'm trying to make this simple. So this method 1 would work for any type of determinant. For any one larger than this, it would work still. Basically, you do plus, minus, plus on the top row, and so in the next row you do minus, plus, minus, plus, minus, plus, if you really want to. You only need one row or one column for this. So you just do plus, minus, plus that way, minus, plus, minus. But basically, the point is, we'll do the top row, the most generic one, if you just want to remember plus, minus, plus, we use this method. And as I tried to color code it, you do x1 times x1 here. So you do like 2 lines across, vertical and horizontal lines to it. You basically eliminate this part of the thing. And then you do y2 times, you basically do a 2 by 2, but you'll see that in the next page. Yeah, basically you're just focusing on the area that's not by the line time. So green, there was a t, so these ones were involved, and you just do it where it's y1 z3 and y3 z1, similar to the 2 by 2 where it's subtraction of the, but it's, you know, basically, and then finally this one is not, you know, you basically do this point of the intersection x3, the point of the two lines, multiplied by this. Now method 2 this only works for 3 by 3 determinants. Basically makes 3 diagonal, you basically add the first 2 columns to the right side, so you have 5 total columns. You copy just this, you copy them, and you do 3 diagonals this way and 3 diagonals that way. And as I color coded them, you add the first 3 diagonals, the multiplication of those 3 terms in each diagonal, and you add them, then you subtract, like I showed with color coded and everything. Now, real quick, let's just briefly discuss method 1 again. By the way, I recommend this method. I'll say that again several times. Use this method for Calculus 3 based material. You really see only 3 by 3 determinants. in this type of course. And honestly, it's easier, I think. It's easier to use this method if it's available. But yeah, more details, method 1. So this is like a little bit more, so you basically have it. These are basically 2x2 determinants. If you had like a 4x4, you'd basically break it down into 3x3s. You'd have, so then you have 2x2s from that. The idea is that this works every time for larger ones, but for the 3x3 like it is, you just see this all the time where it goes like this. But yeah, you'd see this in a textbook more likely as another method. And same thing as before, and you can check these, but you get the same thing. Like that's the neat thing, as I was saying, though. You can solve it in any order as long as you keep your signs right. Like, oh, I decided to go negative x2, y positive y2, and z2. Basically, I wanted to go in this vertical column, and it works. So you can check and see same answers regardless of paths taken, just need proper signs. But as I say, this is more recommended for a course in linear algebra, I would say, not in Calc 3. But yeah, basically you can check this multiple ways, but as long as you get these signs right, plus minus plus, minus plus minus, plus minus plus. No, for plus minus plus you just need one row or one column. Basically you need one row or one column, correct? Then you're going to do this through that column or row. There's a lot you can mess around with this if you really have the time to do it, but I think it's very significant that you understand that determinants are how you're solving cross products in this course. So now let's do some examples. So for first couple, find length and direction of u cross v and v cross u in the following. Basically, so we have u equals 2i minus 2j minus k, v equals I minus k. And I just use this method because I think it's the best method for Calc 3. So I use it 3x3, so I add the columns and I do my diagonals. I color coded for at least these first couple examples. A couple times I use it. Try to keep it color coded so it's easy to understand. But yeah, subtractor takes up some space. You do your multiplication and then addition subtraction, and you get 2i plus j plus 2k, and that's the vector for u cross v. And the magnitude, of course, so we want length and direction, so we do basic square root problem. We do it, and you get 3 as lengths. And now u cross v over the length, so the magnitude of u cross v. If you basically do this division, it'll give you the direction, as you know from previous sections. At this point, you know that from last section in particular. But yeah, there ain't much to say. It's the same. It's mostly the same as before, besides that determinant here. But you just have to follow along. And so v cross u and u cross v are very easily related. If you know one of these, you can easily get to the other one if you really want to. This one I decided to show it though. V cross u equals negative u cross v, basically. Negative of those things. After you take, u cross v, basically. And I'll show that later on how to do it, or at least but that's a shortcut. I don't think you'll usually have to calculate both of them anyway, because that relationship, but if it ever comes up, it can happen. But for this example, again, color coded, like I said, I try to do it. You write it out, paying attention that the first one goes in the second row here, and the second one goes in the third row, because of I, J, and K. Going in the first row. And just they have the same magnitude, you can tell, and of course negative 2/3 I minus 1/3 j minus 2/3 k is the direction of v cross u with the same magnitude or length. So it's this one. So 2i plus j, 2i plus j plus 2k, negative 2i minus j minus 2k. Those are the cross products themselves, as you can tell. Yeah, the negatives of each other. So this is another example. It's the same concept, finding u cross v and then v cross u. But basically you find these because you want to find the length and direction of them, of u cross v and v cross u. But first, yeah, so basically we do you have to find the cross product first to do any of that. And in this case, you do all the mass and you get 0i plus 0j plus 0k technically. You have all these 0k, 0i plus 0j plus 0k. We're going to emphasize it in this case. So yeah, the magnitude, the length slash magnitude of it will be 0. Which is quite obvious, but then that means there's no direction as it's equal to 0 to magnitude. Yeah. And v cross u is equal to negative u cross v, which is equal to negative, 1 times this thing, so it'd be, well, it's the same exact same because it's 0. It's all zeros. 0i, 0k, and 0j. A little mistake there. 0j should be before 0k technically. Improperly ran out. Well, let's just ignore that, it's 0. Here it is. Properly done. You can do the cross product again, but as you can see, I hope you get it by this point. Basically, it's just crossing down, passing. The determinant's not too hard to solve, is it, when you get through this? You just have to slowly observe it. Here's another type of problem. Sketch the coordinate axis and then include the vectors u, v, and u cross v as vectors starting at the origin. Yeah, very brief. If you have u equals I and v equals j, u cross v is going to turn out very quickly to be just k. So u cross v equals k, and just briefly, if you have I, j, and k, that's just your coordinate axis, basically. They go along. I, j, and k go across the respective coordinate axis, and that's it. Yeah, this is basically just a very simple example that meant to demonstrate that you can draw these out in a graph, but it's not usually the most common thing to do in a calculus course. Do that too often, at least. So 1517, we want to find the area of the triangle determined by the points P, Q, and R that are given, and find a unit vector perpendicular to plane PQR. So 15, P of 1, negative 1, 2, Q, 2, 0, negative 1, R, 0, 2, 1, and draw. Point is that PQ times PR will equal a vector perpendicular to plane PQR. So we go from there. We just have to first create the vectors here, though. PQ, like before previous sections, you end up with I plus j minus 3k, and if you do the same as PR, the R points minus the P points, the P, R components minus P components, Q components minus P components, you get these two vectors. Okay, so as I was saying, we have PQ and PR are two vectors, and equal to I plus j minus 3k and negative I plus 3j minus k. PQ cross PR, again, just I was trying to cut this short, this part, because it's the same thing, the determinant. You basically do your 3 lines that way, 3 lines that way. At this point, you should do this, try doing this on your own, basically. But no, now it's time, okay, to actually get into the answers, though, once we get our 8i plus 4j plus 4k. The area equals 1/2 times the magnitude of PQ cross PR. So area equals 1/2 times square root of 8 squared plus 4 squared plus 4 squared, because it's 8, 4, and 4. You eventually get square root of 96, which is equal to 4 square root of 6 for simplification's sake, and that's basically equal to 2 square root of 6, so that's your area. Your area is 2 square root of 6. And the unit vector perpendicular to PQR. So there's actually 2 possibilities. To incorporate both of them, we just have to think about this old plus or minus symbol, but basically you have the PQ cross PR divided by the magnitude of PQ times PR, and also PR cross PQ divided by magnitude of PR times cross PQ. Remember, the magnitudes are going to be the same for both PQ cross PR and PR cross PQ regardless. And it's going to be negative. PQ cross PR will be PR cross PQ. So basically, these other two is positive PQ cross PR divided by magnitude of PQ cross PR, and negative PQ cross PR divided by the magnitude of PQ cross PR. Okay? So pretty much I'm just going to say this, like, for this type, just include your plus or minus at this point outside of it all, and then calculate it. You have your 8i from here plus 4j plus 4k divided by 4 squared root of 6. No, 4 squared root of 6 comes from this part, the magnitude before we multiplied by 1/2 to get area. So basically, that's all you have to do. Is just simplify it a little bit by dividing out 1 divided by square root of 6, so it's plus or minus 1 divided by square root of 6, 2i plus j plus k. And the same thing with this part of the problem. 3 different points now. I plus j plus k is pretty simple for PQ, and PR will be I plus j plus 0k, so there's even a 0 to that. And you get negative I plus j, and you just go through the same process before. Area is 1/2 times this magnitude of PQ cross PR, which is square root of 2 basically, times 1/2, so square root 2 over 2 is the area of the triangle. And PQ basically plus or minus this, and then you get 1 over square root of 2 times I minus j is what one answer, but you could also say negative I plus j if you want to keep how it was originally, how I had it. It was minus 1 over square root of 2, because basically with how these are written, these would be the same thing. Doesn't matter which one, which one's which. So real quick, just the box product or triple scalar product or whatever you want to call it. Whichever term, basically you want to find the volume of the paralleloptic box at the end of this, W, V, and W, and also want to verify this relationship basically. So first do the verification. So just calculate each one individually using the triple product as showed. You can calculate distinctly the 3 ways. The box product. Basically you do that. You get negative 4 plus 1 plus 0 minus 0 minus 0 minus 4 equals negative 7. V cross W times U, same thing, you end up with negative 4 plus 1, negative 4, and then zeros from that, and then equals negative 7. And again, you do your diagonals, or you do it the other way if you want to try doing it the longer method. And this works out. So you get negative 7, negative 7, negative 7 every time. Now the volume, obviously volume is a positive quantity. You can't really have negative volume. So that's why volume is as referenced in the book. You have to take the magnitude of this product, which equals 7 units cubed. I just added units cubed because it usually would have some kind of cubic unit attached, be it cubic milliliters or cubic liters or whatever you want to call it. Heck, cubic gallons could be possible, I guess. Since we're in the United States, anything is possible with what unit would be used. It's some kind of a volume-based unit. 7 of them.